All right, welcome back. This is Mr. Wakefield looking at part 2 of section 7.5. We're now going to do problems 3 and 4. 4 is on the back. And first things first, looking at number 3. And by the way, just to clarify, these dots right here are multiplication symbols. I know the dots are a little bit bigger than you usually are used to seeing for a multiplication dot, but those are meant to be multiplication symbols right there in between the 7 and the 8 on each one of those terms. So let's get into it. As always, like we did in the first two problems, we start out by proving the first statement or verifying the first statement. And that means to take the first term, the part that's before the first plus sign, that's outside of any parentheses, and that would be 7 times 8. Okay, so the first statement again is the first term on one side, and then on the other side you just plug in the number 1 wherever you see the variable n. And so there it is right there. Is this true? Well, again, yes, it definitely is true, but you need to imagine yourself trying to prove it to somebody that's not convinced. Okay, so we figure out what each side's equal to. This side's equal to 56. This side is equal to parentheses come before exponents here. I'm sorry, well, they do, but parentheses come before multiplication. There's no exponent there other than on the inside of the parenthesis that we already dealt with there. And so we end up getting 56 equal to 56. And so we have proven carefully step by step so that a person that was otherwise unconvinced would now be convinced. We've proven the first statement. Part B. Part B again is to what? It is to then write down what we call SK. And so that would be what? That would be plugging K into wherever you see the N, and that's all you got to do, okay, on that. So let's write that down. 7 times 8 plus 7 times 8 squared plus 7 times 8 to the third, dot, 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 all the way up to 7 times 8 to the K is equal to, and then on the other side of the equal sign, same thing. You just plug in the K wherever you see the N, and that is SK, the part B statement. SK plus 1, that's part C. What do? Same thing as the previous two problems. You take the part that is on the left-hand side of the part B statement, and you just bring that straight down. You just copy it straight right off of what you see there in part B, okay, which is exactly what I'm doing right now. Okay, just like that. I took this thing right here again and I brought it straight down. But before we put the equal sign here, remember we have to then add what we would get if we plugged K plus 1 into this last thing right here after the last plus sign right there. And we get what there? We get 7 times 8 to the K plus 1, because we got to plug the K plus 1 now into the N. And speaking of plugging in K plus 1, you have to do that same thing on the other side. Again, we did that in the first two problems, and you get this right here. So that's the part C statement. And then just like we did in the previous two problems, the trend stays the same here, is we now what? We now take the part B statement and we just rewrite it down here in part D to start out. But we leave some space before the equal sign to add that red thing that I was adding to both sides, okay? I'll remind you again of what exactly that thing is. But there is, again, the left-hand side of the part B statement brought down. And then we need to add, and I'll get to that in a minute. Let me put down the other side here first. And then the right-hand side of the original B statement comes down here as well. So these two things on the left side and on the right side we can assume that they're equal. Okay, and then what we got to do in order to prove what we need to prove here for part D is to then add what to each side. What was that red thing that I added each side on the previous two problems? It was always the last part of the part C statement so that the left-hand side of the part C statement would look exactly the same. The right-hand side is not going to look the same right away because you got to add the same thing over there as you added over here. You don't just plug in k plus 1 again. You just add whatever you add over here to make the left-hand side of the part C statement the same. In this case, it was plus k plus 1 to the third, this last part right here. You add that same thing to the other side. What is that thing going to be in this problem? Well, this is the last thing on the left-hand side of the part C statement right here. Right here. So that's exactly what you need to add to both sides. 7 times 8 to the k plus 1 power. Okay. Like that. Okay. So then what's our goal? Whenever we add that same red thing to both sides, our goal is to then prove that this thing right here, the right-hand side of the part D statement, we need to prove that that's equal to the right-hand side of the part C statement. Okay, that's always the most challenging part of the problem. Okay. So how are we going to do that? Well, notice in the part C statement, again, we want to make it look like this. That's the whole goal. Okay, to prove that it's equal to this, we want to make it look like this so that it'll truly be the same. It'll be equal. So notice that there's an 8 on the outside. We have an 8 on the outside here, but the bracket that's next to that 8 right there only covers part of the problem here. It stops right here. It doesn't go all the way over to here. So what I need to do is I need to factor 8 out of the whole thing, because right here I have 8 times a bracket that then goes to the end. So that 8 works for the whole thing. This 8 right here doesn't. It just works up to where this bracket ends. So what you need to do is go like this. Write down the 8. And I'm going to factor it out of not only this part, but also this part. Okay. And if I do that, as you know from that first part right there, it is 8k minus 1. Okay. 8 times 8k minus 1. If I factor out the 8, the inside part here will just be the 8k minus 1 part. Okay, then you bring down the plus right here. Okay, just like what we do when we normally factor out a GCF, you break it up according to any plus or minus signs that you see outside of a parenthesis. Okay, this minus doesn't count. Outside of a parenthesis, also this plus doesn't count because it's inside of an exponent. It's just a normal plus or minus sign that's outside of a parenthesis that breaks the problem up into different parts that you would factor from. So when you factor out the GCF, because you got that plus right there, and that's the only plus or minus sign that's outside of a parenthesis, it's not in an exponent either, okay, that breaks the problem up into 2 parts, and so you're going to be factoring the 8 out of these 2 parts right. That's why I underlined these 2 things. I just wanted you to know why I broke it up into these 2 parts that I underlined. Okay, that's how I knew to break it up that way. It's because of that plus that's outside the parenthesis. So 8 being multiplied by that in the first part that I underlined. Here, this is a little bit of a trickier thing. Let me pull out a piece of scratch paper to help you understand better. 8k plus 1. 7 times 8k plus 1 in particular. I need to factor an 8 out of that. Please remember that 8k plus 1 is the same thing as 8k times 8 to the first. Because remember, when the 2 bases are the same, you guys, and this is going back to reviewing exponent rules, when the 2 bases are the same, like if you had x and x, for example, wouldn't you add the exponents like this? It's no different here. It just looks weird because you have a variable in your exponent. But if the 8 and the 8 are the same, that is the same thing as this. You're adding the exponents when the bases are the same. And so going backwards, trying to break this the 8k plus 1 apart into 2 separate parts, you got 8k and 8 to the first, because we know that these 2 things together are equal to this. Okay, so let's rewrite this now. This is what we got right there. Okay, why did I do this though? I mean, we understand now why the 8k plus 1 right here is equal to these 2 parts together. Okay, we understand that, and then the 7 just came over. But why did I do it, though? I did it so that I can factor that 8 out of there. Okay? So let's look at that side by side right here. Okay, if I want to factor the 8 now out of that, okay, which I did, I pulled it out in the front. Wasn't it true that 7 times 8k would be what you'd have left over on the inside? Because you pulled the 8 out to the front. That 8 right there is now here. That first power, you don't need to write that anymore because 8 to the first is the same thing as 8. So I took that thing and I pulled it out to the front right here, and then 7 8k is what you got left over on the inside of the bracket. Okay, so I got the 8 on the outside. So now can I prove that the inside of the big bracket right here is equal to this? I can. Let me show you how. Okay, again, I need you to listen carefully here. It's a little bit complicated. 8k and 7 times 8k. All right, remember, and I'm going to do this a little bit of a different way here to help you relate it to something you've already seen before. Pretend like the, let me write it down right here, 8k and 7, and I'll bring in the -1 here in a little bit. Okay, we don't need to worry about that right now. But look at the 8k and the 7 8k. All right, I want you to pretend for a moment that the 8 to the k power is the same thing as x squared, because we're used to dealing with stuff like x squared. Okay, if that was the same thing as x squared right there, then wouldn't this be x squared plus 7x squared? And we know how to combine those terms, right? Wouldn't that be 8x squared? Here's the thing, you guys. This doesn't have to be x squared right here. If these two things are the same, you guys, if you've got something plus 7 times that same something, it doesn't matter what that thing is that I circled. It could be anything. It could be no matter how weird it looks. Okay, if you've got something plus 7 times that same something, okay, it's just like doing x squared. You can combine that. All right. So just like x squared plus 7x squared is equal to 8x squared, this is equal to 8 times 8k, because 8k and x squared are the same thing here. These two things are the same thing. All right. 8k was meant to be the same thing as x squared here. I just showed you x squared, though, to help you relate it to something that you already know how to combine. But rest assured, though, you guys, if these two things I circled are the same, you can add the invisible one that's in front of this one right here and the plus 7 to get it equal to 8, just like you did 1 plus 7 equal to 8 on this one down here. Okay? So for that reason, I can then combine this part right here and this part right here to get 8 times 8k. And then the -1 doesn't combine with anything, so I'm just going to bring that down. I'm pretty close to getting it to look like this, aren't I? What is 8 times 8k? We just found out a few minutes ago that 8 times 8k is 8k plus 1. And we have proven it. We now have made it look like this. Without saying, oh, hey, it's obvious, okay, you should understand. No, you did it with very detailed steps here, one step at a time, so that if somebody wasn't convinced, they now would be convinced. Okay? And so that's part D. What's part E, you guys? The exact same thing as part E up here. Okay? You just rewrite that same thing. I'm going to go ahead and rewrite it again for practice. Okay. Whenever SK is true, what do we say? SK plus 1 is also true. All right. And what does that mean? That means that since S1 is true, S2 is also true. You could just say true. Also is just being overly, given overemphasis there. All right. So since S2 is true now from the previous sentence, we now can say that S3 is true. If S3 is true, we can then say what? S4 is true. Again, I know that we know how to say this now. We said in the last two problems, but just for practice. And so on. It goes on forever, in other words, all the way to S infinity, if you want to call it that. but it works for any number, any of those positive whole numbers. Thus what? Sn is true for what? Is true for all n. And you don't need to underline the word all like I did last time, but you could if you want. All right, so that is part E right there. Okay. All right, so that is number 3. Again, go through the steps detailed. All right, you're going to have a problem that's just like this on your homework. All right, the only difference is that they changed the numbers slightly. I'll get into that here at the end. Okay, so you just got to follow the same kind of steps. I'll show you that problem, in fact, when we get here to the end. Let's do this last problem first on the back. Number 4. Okay. Again, what are we doing first in any one of these 7.5 problems? We first of all prove it for S1. S1 means what? You take the first term that goes before that first plus sign that's outside of any parenthesis. Okay. And that would be 1 over 1 times 4. On the other side of the equal sign, you just plug in 1. And so we get 1 over 3 times 1 plus 1. We already know this is true, otherwise it would not ask us to verify it. Okay? But we just need to prove that it's true to somebody that doesn't believe it. 1 over 1 times 4 is 1/4. And then as you can see here, 3 times 1 is 3, plus 1 is 4, and we just proved it. Okay? Both of them clearly are equal to 1/4 just by doing order of operations on each side, just like we did in the previous problems. Part B. Write out the SK statement. So let me go ahead and do that. Just plug in the K, that's all you got to do. Okay, so in this last fraction before the equal sign, we get 1 over 3k minus 2. And then 1 over 3k plus 1. On the other side of the equal sign, you plug in k, and you get k over 3k plus 1. All right. Next one, part C. Again, the same thing we did in the last 3 problems. You take the entire left-hand side of the equal sign, and you just bring that down. But then we add something to that. But let me go and bring that down first. Okay. Just transferring that thing straight down from the last step, part B. And then just like we did in the previous 3 problems, we then bring down another plus there, and then we plug k plus 1 into this last thing here that's after that last plus sign. So we need to plug in the k plus 1 right here to get that last part there, just like we've been doing in the previous problems, and that gives me what here? If I plug the k plus 1 into that last thing that's after that last plus sign there, I get 3k plus 1. Use the parenthesis because you're plugging the k plus 1 into a variable, and it's got 2 terms, so you especially need it. Not that you wouldn't need it in other situations usually, but definitely when you got 2 terms, when you're plugging 2 terms into something. So there's that right there. I plugged in the k plus 1 into this. Remember, as I said earlier, when you have a smaller bracket inside of a bigger bracket, you can distribute that out first. So we get 3k plus 3 minus 2 in that first bracket. In the second bracket, I got 3k plus 3 plus 1. Then I can go ahead and combine like terms, just to simplify this a little bit. And that leads to what? That's going to lead to 1 over 3k plus 1 in that first bracket. This first bracket right here becomes 3k plus 1. And then the second bracket right here becomes 3k plus 4. Like that. And so that's exactly what would go here. And then, just like we always do in part C, on the other side of the equal sign, you would then plug in k plus 1 into here. If I do that, I'm sorry, not into there, you plug it into here. Don't plug it into here because then it would get all confusing with the k already being there. Plug it into the original problem, as we always do in part C from the when we did that previously in the last 3 problems. Plug it into here. So the k plus 1 goes into the n, like that. The k plus 1 goes into here. I'm going to go ahead and simplify that right now because that's going to help me later. You're welcome to do that. When you plug a polynomial, when you plug k plus 1 into just a normal polynomial there, and there's no exponents or anything, that would make things a little bit different, but there's not here. You can just distribute and then combine like terms when that happens. Okay, again, when there's no, if it's n squared, it's a little bit more complicated than that. But since it's just n to the first power and there's no exponents, all right, you can just take what you plugged in, distribute that out with the 3, and then combine with the 1. And so that would become what here if I did that? That would become, let me just write it down up here so you can see later on when you look at your work where this came from. This is what we got. Okay, and then it becomes what? It becomes 3k plus 3 plus 1. And ultimately, when we then combine like terms, you get 3k plus 4. Okay? Okay, so as usual, as we go on into part D here, we take the part B statement, bring it down. Just give me a moment to write that down. And remember to leave some space to add the appropriate thing to both sides. Okay. And then put the other side of the part B statement over here. And then what is that thing that we always add to both sides? It is always that last thing that is on the left-hand side of the part C statement. In this case, it is this thing right here. 1 over 3k plus 1 times 3k plus 4. But you got to add that to the other side too. Okay, like this. There we go. Like that. Let me zoom out. There we go. Now, what's our goal? As always, our goal is to take this thing right here, the right-hand side of the part D statement, and to make it equal to this. In other words, make it look like this. Okay, simplify it so that it looks like this, and then you'll have proven that it truly is the same since it looks like it. All right. As you can see here, we got 2 fractions, and here you got 1. As we saw earlier in the first couple problems, when you got 2 fractions, you want to make them into 1, and they're being added together. Then do just that, add them together. Okay. You can see here that the common denominator, because we have a single prime factor here, and then here we've got 2 prime factors. As we learned back in the prerequisite review packet, when you got those prime factors that have 2 terms in them, or more than 1 term in them, in this case it's 2 terms, you put all the different ones into the LCD. Okay, you can see here, for example, I had y plus 2 occur in both of the denominators, and then this one just appeared in one of them. Okay, but none of them ever appeared more than once in the same place, and so you just simply put them both into the answer 1 time each. The y is different because that was a single term factor. We don't have one of those here. But just want to remind you of that to help you realize that the LCD is going to be 3k plus 1, 3k plus 4, because you got to put them both in there since they're both factors in each one of your denominators. Let me just write that down. But yeah, you can review the LCD discussion in the prereq review packet. That definitely talks about that in more detail. Okay. So this one already got the denominator you want, so that stays the same. That fraction stays the same. Here, don't you have to multiply this one by 3k plus 4? And the reason why you do is because the 3k plus 1 is already down there. If I multiply that by 3k plus 4, it would then be equal to the denominator that it needs to be equal to here. The denominators would then be the same. So since that was already there, 3k plus 1, I now multiply by that, and it'll now be the same denominators. But because I multiplied the bottom by 3k plus 4, you got to multiply the top by that too. Okay, that's part of adding fractions together, right? You got to multiply the top and bottom by the same thing in order to make the denominators the same. Now, just like I did in the very first problem, because we don't have an exponent attached to the variable here, usually it's good to go ahead and distribute that out, usually. And what do we get there? We get... before we combine like terms, we want to distribute that out, that is. I get 3k squared plus 4k. And now that the denominators are the same, okay, I can now combine the numerators together. That means to combine any like terms that you have. However, the numerators do not have any like terms, so what do we do in that case? We saw this even not that it's the only time we've seen it this semester, but we saw it earlier in this section. Can't combine those together, so we just say that they are being added together. In fact, write it in this order, because this looks like one of those Berry method factoring problems where you got the k squared first, and then the k, and then no k at all. And so we want to go ahead and write it like that, and then try to factor that. If I factor that, I do 3 times 1. 3 times 1 is equal to 3, but I need the two numbers that I pick to add up to 4. Well, wouldn't that be 3 and 1? Okay. But the Berry method says what? It says to go, if it's 3k squared in the front, we need to say 3k and 3k. So we get 3k plus 3 and 3k plus 1. Again, review the factoring portion of your prerequisite review packet if you need to. But then we need to factor out the GCF out of both of these if they're not equal to 1. Well, this one has a GCF of 1, so that stays the same. This one has a GCF of 3, though. So what we do is we factor it out. If we factor out 3, we get k plus 1. And then in the last step of the Berry method, remember, you throw out any GCF that you factor out. So that whole factoring thing on top becomes k plus 1, 3k plus 1. And this is great news, because the 3k plus 1 on the top and bottom are now going to cancel out. And guess what we end up with? We end up with exactly what we wanted to end up with, okay, which is the right-hand side of the Part C statement. Let me zoom out so you can see it all at once. There is the right-hand side of the Part C statement. We wanted the right-hand side of the Part D statement to look just like that, and now it does. Because we went through our normal process of adding the fractions together, okay, and doing some factoring, all right, just like we've done on some of these other problems. Okay, so again, each strategy here when you do the Part D is different, okay, but your homework problems, as I'll explain in a minute, are quite similar for the most part, so that'll be helpful, okay, as far as the strategies you use on Part D. So, but again, what is Part E? Okay, whenever what? Whenever SK is true, don't forget to say that. Don't jump right into that S1, S2 stuff. Okay, because you need to point out that Whenever one thing is true, the next statement is automatically true. And by saying SK plus 1, you are saying that that whole concept of one statement being true automatically means that the next one's true. You're saying that that is going to hold for all possible statements, not just S1 and S2, for example. All right. So what does this mean again? It means that since S1 is true, S2 is true automatically. Since S2 is true, S3 is true automatically. You don't have to say automatically, but I'm just emphasizing that idea. Since S3 is true, S4 is true automatically, and so on. Again, please use these exact words, you guys. Okay, that way I'll know absolutely certain that you understand. Whether you're doing homework or the exam, use these exact words. If you divert from that, again, what's important is that you prove this to somebody that's a skeptic, that is not convinced. Okay, if you divert from it, as long as you're proving it to somebody, that's fine. But I know that you're just learning this for the first time, so I would highly recommend, in order to not take any chances, to just use the same words I've been using, okay, in order to make sure that what you're trying to point out is exactly on the mark with what needs to be said, okay? Thus, SN is what? Is true for what? For all n. Okay? And that concludes the last problem right there. All right, so as you can see, once again, all these problems are basically the same process except for the method that you use to prove that the right-hand side of Part D is the same as the right-hand side of Part C. That process is different for each problem, as you've seen. Okay, let's take a look at your homework before I stop the video here. Homework I'm going to assign is this: 9, 13, 15, and 17. Okay, let's take a look at those one at a time. You'll see that number 9, and let me pull out the worksheet here so I can look at it side by side. Number 9 is extremely similar to number 1. Okay, the only difference is that instead of the 5 being there, they now have the 3 there. But you can see that they look almost identical otherwise. And so the process for doing number 9 will be very, very similar. Please refer to number 1 to help you. Number 15, I'll come back to 13 in a minute. Number 15 looks very, very similar to problem number 3. Okay, the only difference is that instead of having the 8 and the 8n, you have the what? You have the 6 and the 6n. So it's a very similar thing. It's just instead of 8, you got 6s. Okay, and also you got 5s there. Okay, but that's not going to be overly crucial. The point is that you're going to be doing the same thing in Part D with the 6s that you did with the 8s right here. Okay, so if you do the same thing here, but just with the 6s instead of the 8s, you should be okay. All right, let me know if you're not. Number 17. Number 17 is very similar to the problem that we just did, where you're going to be able to get a common denominator. Okay, you're going to be able to get some factors to cancel, and it'll end up looking like it's supposed to look at the end. Okay, that same type of thing will happen here. Okay, in number 17 in Part D. Finally, back to number 13. That one's a little bit different, but one thing I will tell you is that when you get to the Part D statement, remember in problem number 2 where I took the brackets and I treated them like variables? In fact, I'll pull out the piece of scratch paper that I did earlier so that you could see that. Here it is right here. Remember when I treated the brackets like they were variables? I factored out the GCF, and then I put the bracket back in the place of that same variable again. You could do something similar to that on number 13 if that helps you. Okay, go ahead and try that. Again, that's in the part D, not before that, but in the part D part, where you're trying to make the two things the same, okay, like we've been doing on all these problems. Think about that strategy. You'll have two different brackets in that case, but if you think of them as two different variables, like if you use like y and z instead of just z, okay, go ahead and try that. And you should be able to eventually prove the part D part, okay? Again, let me know if you have any questions, all right? But yeah, definitely take advantage of my office hours. They are listed in the syllabus. Okay, I've mentioned them before. And so if you're stuck on anything, all right, please let me know. Again, yeah, look at those times so that you can take advantage of those. All right, but yeah, like I said, those little clues I just gave you there, the tips, the fact that these are similar to some of the problems we did in the worksheets to certainly help you as well. Okay, but that concludes section 7.5. Okay, again, let me know if you have any questions about what I just talked about or anything else. Okay, you have a good day and you take care.